Now let's begin working on an actual problem. We're going to do this exercise. Determine if the following system is consistent. If it is, find a solution. So you can see here we have a system of 4 equations and 4 variables. At its most elementary level, linear algebra deals with solving systems of linear equations. There's a lot more to linear algebra than that, but this is going to be our starting point, solving systems of linear equations. In the world of data science, programmers often have to deal with systems that have thousands of equations and thousands of variables, and there are all sorts of programming issues about how a machine can work through the steps to solve those. We're not going to look at the programming issues, we're just going to look at the mathematical, theoretical side of things, and we'll usually work with just a few equations and few variables. The first thing we want to do is set up a systematic process we can apply to solve these systems with lots of equations and lots of variables. And it's like we need something a little bit more than just basic algebra to help us get through. But actually the process is fairly simple. We're going to work with something called a matrix. And for every system, there's something called the matrix of coefficients. Now a matrix is a word that comes up a lot in linear algebra. A matrix is a rectangular array or arrangement of numbers. It's just a way of organizing numerical information. For us, it will be a way of organizing the information from this system of equations. The plural of matrix is matrices, so try to get used to that. So the matrix of coefficients here in this problem is an arrangement of the coefficients. And what I'm going to do is I'm going to write these coefficients in square brackets, giant square brackets. And I'm going to start out with the coefficients of x1, which are 1 from the first equation, 2 from the second. And because x1 doesn't occur in the third or fourth, I think of its coefficients as being 0 in the third and fourth equations. So I have 1, 2, 0, 0 as the coefficients of x1. Then come the coefficients of x2, 1, negative 1, 1, 1. Then the coefficients of x3, the third variable, 1, 0, 3, 2. And then the coefficients of x4, 1, 5, 0, negative 1. So there's a matrix, the matrix of coefficients. So you need to know that this first column stands for the coefficients of x1, the second column the coefficients of x2, then x3 coefficients, then x4 coefficients. That's the tradition we're going to follow. Now, we're actually going to work with a slightly different matrix most of the time. We're going to work with something called the augmented matrix. And the augmented matrix is just the matrix of coefficients with something added on. It's been augmented. So we start out with 1, 2, 0, 0, 1, negative 1, 1, 1, 1, 0, 3, 2, 1, 5, 0, negative 1. And I'm going to add another column of numbers. When you look at our system, so far I haven't written down any of the constants on the right. Clearly 4, 1, 0, 1, these numbers on the right are important and relevant in solving the system. So that's what I'm going to write down in another column, 4, 1, 0, 1, the constant coefficients from the right-hand side of those equations. And what we see in the augmented matrix is really all the information about that system is there, and we're just going to work from that matrix to solve the system without even writing the variables down. Now, a little bit more terminology. We talk about matrices as having rows and columns. So there's like a row 1 going across, a row 2, row 3, row 4 going across. But then as we go up and down, we talk about column 1. I'll abbreviate that, COL, column 2, column 3, column 4, column 5. And when we refer to a matrix, we always talk about the number of rows and columns as its dimensions. And we always give the rows first. So this augmented matrix, we would write 4 by 5. We write a little X in between, but we read that by using the word by here. And so we call this a 4 by 5 matrix is the augmented matrix. So that tells me exactly what its size is. In general, an M by N matrix has M rows and N columns. So we traditionally use those letters M and N to designate the number of rows and columns in an abstract sort of way. Now, I think so far we've just talked a little bit about the terminology and the vocabulary. We're ready to go ahead and start solving this system, but I think I'm going to do that in another segment. So that to be continued will actually solve our system now that we have this vocabulary set up.